Our speaker this evening has previously worked at both HPE and SAP, supporting their database products. Please welcome the Master Data Solutions Architect for MemSQL, Sourabh Mehta.
Thank you. Can you guys hear me in the back? Yeah. Clear? Yeah. All right, wonderful, wonderful. Thanks for making the time. So, my name is Sourabh Mehta. I'm a solutions architect with MemSQL. And what we're going to cover today is an overview of MemSQL, how the architecture looks like, how does it fit in your enterprise, where do you leverage it in between your OLTP and OLAP layers. And lastly, we'll talk about some examples of how MemSQL is used in financial services, and I'll also show you a demo. All right, sounds interesting? What I'd like to do as part of this presentation is make this interactive. I don't like to wait till the end for questions because then it gets boring and I'm just talking to you. So if you don't mind, raise your hand and ask me questions as I'm going through, and we'll make the session interactive. I'll answer your questions as we're flowing through the slides. Game? All right. So this is how the slide deck is broken down. It's Accelerate Your Enterprise, which talks about MemSQL's architecture and what are the differentiators of MemSQL. The next section is Simplify Your Architecture, which talks about how MemSQL can help simplify your enterprise architecture. And lastly, Win with MemSQL are examples of MemSQL driving financial services industry and how it's basically helping serve their real-time needs. So, what is MemSQL? What does it do? So MemSQL is what Gartner calls an HTAP database. How many of you have heard of HTAP? Right. So just like Gartner does, they've defined something that already exists in the industry. What they've defined is a technology stack which services OLTP and OLAP workloads. Right. So hybrid transactional and analytical processing engines are called HTAP databases by Gartner. Traditionally, you would have OLTP databases at one end of the spectrum and OLAP databases at the other end of the spectrum, different sets of users with access both. And then you have lags that occur moving data between one system to another, ETL processing and everything else. And then finally, your end users basically who are doing analytics get access to the analytical data set, right? So MemSQL collapses those layers into one. And so you can do OLTP and OLAP in the same engine. And so that's a massive differentiator for us. In addition to that, we do real-time processing of data. So you can trickle load, stream load, batch load data into MemSQL on the fly. And you do not have to wait till certain times in the day where you batch your data and load that into MemSQL. So that addresses the 3 points up here: scalable, streaming ingest. So we scale out. I'll talk about these concepts on the following slide. So we scale out. You can do database workloads. You can do data warehouse workloads in MemSQL. Questions? All right. What I'll try to do is, towards the end of every slide also, I'll pause and ask if there are any questions in case you have some pending questions there. So ecosystem overview. This is how MemSQL fits into the ecosystem in your existing enterprise. So if you look at my right-hand side, your left-hand side of the slide, it talks about how you get data into the database. So if you have data coming in through Kafka, we have integration, Kafka integration, we have Spark integration, we have S3 integration, we have Azure Blobs integration, we have HDFS integration. There's different sorts of integrations available for you to ingest data from different platforms, right? So in the case of Kafka as an example, or whether it's a file system, right? We provide once and only once semantics when ingesting data. So if you're ingesting data from Kafka, if we ingest an offset successfully, we will not try to ingest the same offset again. If you're ingesting a file from a file system, we will ingest that file only once, and then we'll never ingest it again to ensure that you're not duplicating the data that you're loading into the database, right? We have Spark integration because MemSQL scales out, Spark scales out. You can load data in parallel from Spark into MemSQL. You can pull data in parallel from MemSQL into Spark. So you can leverage the MPP capability of both systems. So that's how the left-hand side of the ecosystem looks like, right? So left-hand side talks about how you put data into MemSQL, right-hand side talks about how you pull data out of MemSQL. So if you have existing tools that you want to use, you have Informatica or any other ETL tools that you want to leverage, MemSQL is MySQL wire protocol compliant. So you can use the MySQL adapters to basically connect to MemSQL. So if you're using Informatica, we have a MemSQL specific connector there. If you have a homegrown tool that you want to use, you don't know what connector to use, basically use a MySQL connector or a MariaDB connector because they're basically the same so far. They're going to branch out eventually. But you can use those drivers. Now I say MySQL wire protocol compliant, which doesn't mean that MemSQL is based off of MySQL. It's just using the client drivers to provide the connectivity. So then we don't have to go and test against every single ETL tool and every single BI tool. Make sense? Now, the bottom of the slide talks about where you can run MemSQL, right? So you can run MemSQL on physical hardware. You can run it in virtual machines. You can run it in Docker containers, on Kubernetes. So there's multiple ways in which you can run MemSQL. You can run it on premise. You can run it in cloud. You can run it on one cloud and replicate data from one cluster in the cloud to another cluster in another cloud. So you can replicate from premise to cloud also, right? From our standpoint, all the clouds are providing is infrastructure. So if you have a cluster running on-prem, as long as there's connectivity established between your cloud instance of MemSQL, you can replicate data from a cluster on-prem to a cluster in the cloud, a cluster from in AWS to another cluster in GCP, and vice versa, right? So we do not restrict you from running in one cloud or another cloud. We provide you with the ultimate flexibility. If you go to a cloud and decide to come back on premise, you can do that too, right? So our license is completely portable. So that's a differentiator for us when you're leveraging MemSQL for your enterprise needs, right? So if you go with other solutions, some may tie you into their particular cloud or a particular cloud, or have you required to run in a cloud versus deploy on premise. So that's the bottom of the slide. The other thing I'll address is there's quite a few questions usually that come up, which is, do you guys provide managed services? Can you deploy on multiple clouds? The answer is yes. You can deploy on AWS, GCP, Azure. If you do spin up an instance in some other cloud which is not supported, it's not an issue. As long as the networking and CPU and memory is good, you should be able to run MemSQL anywhere. It's not an issue, right? We also provide a managed service to ensure that if you want to do hands-off usage of MemSQL, you say, okay, we want to bring our data, bring our queries, the remaining administration aspects should be taken care of by you. We do that too. So that's the whole bottom of the ecosystem overview slide. The right-hand side talks about how you pull data out of MemSQL. So there's a lot of enterprise tools that companies use, whether it's Tableau, MicroStrategy, Looker, Click, whatnot. And we integrate with all of them because we have MySQL wire protocol compliance, right? Some companies we work with provide even more closer integration or even better integration. So we have specific drivers available for Tableau for MemSQL because we work with them to ensure that they get the most optimal performance possible. If you have a homegrown BI tool you want to leverage, just use the MySQL drivers and you should be able to connect to MySQL. If not MySQL, then MariaDB, right? So either one of them should work. I'll pause here, see if you have any questions before I build the next concept. So, great question. I'm going to steal my thunder from a following slide and answer your question. We're ANSI compliant, ACID compliant, SQL 99 database. The question is this RDBMS SQL based or something else based, right? So, MemSQL is a ANSI compliant, ACID compliant, SQL 99 compliant database. Any other questions? All right. So you can see in the center of the slide something I haven't addressed, which is streaming ingest, memory optimized tables, disk optimized tables. I'm going to touch upon this going further, but MemSQL provides you with the flexibility to deploy OLTP and OLAP workloads. For OLTP workloads, we store them in memory because you're going to do a lot of singleton inserts, updates, select start queries. For analytical queries, we store the data in our column store, which is our disk-based store. However, there's a caveat to that. Because we're an in-memory database, the first time you access data from disk, we'll host it in memory. And it stays in memory as long as the data is warm. And I'll touch upon why we do that, how we do that, things like that on a later slide. All right, so this was the question you asked. So scalable SQL. So MemSQL is ANSI compliant, ACID compliant, SQL 99 compliant database. You can store JSON data, geospatial data also in MemSQL, and we index that data optimally, so it's not a second-class citizen of the database. You can store that data, query that data at high performance in MemSQL. We scale out. So MemSQL is not a scale-up solution. You can scale out and add nodes. We have two different types of nodes, and you can scale each one of them individually. And I'll talk about what are the different types of nodes also going further. So in this case, we scale out. We run on commodity hardware. We are not an appliance. You do not buy us by a half rack, a quarter rack, a full rack, and you don't pay a crazy amount of money for doing that. So in MemSQL's case, we run on commodity hardware. You come to us, we tell you, this is the amount of memory you'll require, this is the amount of CPU you'll require, this is the amount of storage you'll require, and it's up to you, basically, as to whether you want to deploy an HP, Dell, or any other hardware, right? We have clients running on Open Compute also. As long as you are able to meet the CPU memory disk requirements, we're fine with it. Let's see what else is there. So in-memory and solid state, I'll touch upon that as we go further. Data center cloud, I already touched upon that. You can run us on premise, you can run us on cloud, you can run us on any cloud, and you can replicate between all of them. I'll pause here. Any questions?
How about multi-cloud?
Sorry?
How about multi-cloud?
You can run, so the question was, how about multi-cloud? So multi-cloud is not something that we recommend because of latency issues. So I'll talk about that going further, but we have high availability options. If you try and split a cluster between two clouds, no one can guarantee performance. And if you can't guarantee performance, then trying to keep those two clusters in sync is going to affect your query performance. Query loading, data loading, query performance, absolutely everything is affected. So we do not recommend distributing a given cluster across two clouds. You can replicate from a database in one cloud to another, one cluster in one cloud to another cluster in another cloud.
How is it done? Synchronous?
Asynchronous. I'll touch upon that as we go further also. Any other questions? Comments?
What about cloud and on-prem?
We do that too. So you can
You
deploy us.
also don't recommend it?
What do you? Sorry?
You said you don't recommend multi-cloud. You also don't recommend on-prem and cloud.
We do not recommend splitting a single cluster across any given geography. Whether it's cloud to cloud, whether it's prem to cloud, you can deploy a given cluster in one location and use it there. You can replicate from that cluster in another location, and you can leverage it that way. All right. Any other questions or comments? I see a hand up there.
How readily do you guys pass, first question, what levels of isolation do you force and for, if you're going for linearized code, do you test that in the face of network partition? Because it's a highly distributed database, you actually burn the
Okay, so the question is about what levels of isolation do we support and how do we ensure that we don't have split brain? I'm summarizing. Does that accurately summarize it? Okay. So we provide read committed transaction capabilities. So that's how we take care of your data set. So we also do MVCC. So we do MVCC to ensure that if you're loading data, who's querying, how do you ensure what people are reading, things like that. That's how we resolve that issue. In terms of split brain, I will address that on a later slide if you don't mind, because that'll make more sense. Because now I'll be talking about that concept without any thing for you guys to look at, and it's very abstract then. So just give me maybe 5 minutes. Any other questions or comments? All right. So this is where I'm going to build up the other concepts, right? I talked about OLTP and OLAP. So let's split up those workloads and talk about them individually. So let's say you have an OLTP workload. Typically what you do in an OLTP workload is you will trickle load data a couple of rows at a time, maybe hundreds of thousands of rows at a time, maybe millions of rows, right? Now you'll trickle load data and then you'll run select star queries, you'll run singleton updates, singleton deletes. For those sort of query operations, you use our row store, which is memory based. Now, in contrast to other caching technologies where you're only storing the data set in memory and saying, okay, great, you're accessing in memory and you're faster because of that, we have a lot more optimizations that we do on top of that. So we ensure that we're building lock-free indexes on that data, which is sitting in memory. So we will access the data even faster while it's in memory. Right, so if you're running a query, we'll access the indexes. We build skip list indexes. How many of you know what skip list indexes are? All right, 2 people. All right, so let's step back and say 30 years ago, maybe more, when Oracle and other databases were building indexes. B-tree index was the main index type that most of the databases ended up with. And B-tree indexes, if you look at the theory, anytime you load data, delete data, they require rebalancing because it's a tree structure, right? So you may have lopsided trees and whatnot, which you eventually have to balance out if you want optimal performance. I'm not going into the nitty-gritty of it, but at a high level, that's what it is. You also endure locking and other things because of that index types while you're rebalancing them and doing things like that. With MemSQL, we leverage something called skip lists. Unfortunately, I don't have a visual representation of that, but what typically happens is that you have a primary key that you specify. For the sake of simplicity, let's say you specify a primary key that has numbers 1 to 10. What we'll do is for every single value of a primary key, there's a coin flip algorithm that runs. We will flip the coin and decide the height of that tower. And we'll build a tower for every single value. Once we flip the coin 10 times, we have towers of different values, of different heights, right? For every single value, there's a different height of the tower. So now when you're trying to run a query, we'll traverse the towers based on the heights and get access to your data faster in that manner. What this lets us do is, let's say you decide to delete the number 5. We don't have to rebalance anything, the tower just goes away, right? So your data access methodology remains the same. It's tough to describe. It's easier to look at it visually. If you go to Wikipedia, they have a great GIF that shows how it actually works. So we leverage skip list indexes. What that does is it provides you lock-free access to your data, right? So while you're loading data, because of MVCC and other things that we do, you can keep loading your data, querying your data without any impact on each other, right? So you can trickle load data, you can batch load data, you can stream in data, whatever you're doing. You can keep doing that and continue running queries. Because we provide read committed access, as soon as a batch is committed, depending on when you grab the snapshot or what you're accessing, you'll read the committed data, right? If your transaction is already running, we're not giving you access to that because of MVCC rules. So in terms of OLTP workloads, we store that in memory. We are not going to compress or encode that data while it's in memory because it does not make sense to do that. If we compress that data every single time you run a select star query, we're going to have to decompress that data, right? So that's a challenge that exists if you're basically trying to compress and decompress data every single time. It affects your query performance. We want the fastest query performance possible with OLTP workloads. So you can have a lot of concurrent users coming in, accessing the data sets. So in this case, for OLTP workloads, you have byte-rate indexes. We do not compress it or encode the data. And you can run your select star, singleton inserts, updates, delete queries on your row store tables. Now let's say that we've built a skip list index on a primary key. You want to index further columns in your tables. You can absolutely do so, and you can build additional indexes on that. And that's basically to ensure you get the most optimal performance that you're looking for. All right, I'll pause here. So one question that always comes up with the row store tables is, what happens if I lose power? This is RAM based. Do I lose the data? No, because we're snapshotting, checkpointing, and we're doing all those things in the background to ensure that in case you lose power to your cluster, you do not lose that data set. And we have multiple levels of redundancy, which I'll touch upon on a future slide, right? To ensure that even if a disk fails, or a node fails, or a cluster fails, you still have access to your data set. So that's the row store. I'll pause just to see if there are any questions or comments. All right, looks like everyone understands what the concepts here, so let's move on. Now, that was the left-hand side of the slide. The right-hand side talks about column store tables. Right? If you're looking to do analytics, you would use our column store tables. So this is a table-by-table decision that you make. Right? So your row store is what you leverage for your dimension tables as a simple example. For your fact tables, you use column store. In the column store tables, every single column is stored in a set of files. Each file, when it's stored on disk, has min and max values, right? So we're going to store of all the data in the column store table is going to be sorted and it's going to be encoded. Because we're sorting and encoding that, every single file has min and max values without overlap from the next file. We keep the min and max values in memory, right? So if you're trying to access, say, give me the sales for the East region for the month of January for a guy named Joe Ventura, right? What will happen is it'll basically filter down to the exact set of files that need to be accessed, and it'll basically pull that into memory. You don't need to scan the entire set of files on disk. The data is, index data is sitting in memory. So we resolve that in memory itself. And then we access the files that we're looking for. Once we access the files we're looking for, it phases into memory, and you're accessing that in memory. Going forward, if you come back and say, some other query is running later on, and it's trying to access the same data set or slice and dice the same data set, that data set is going to continue residing in memory. So first in, first out, eventually it's going to phase out if you're not accessing it. Right? So that's the way the column store works. So that touches upon multiple concepts, right? So coarse-grained index, we call it a coarse-grained index because we're not going to an individual value of the primary key. We're going by the min and max values of a given file. Min and max ordered columns, that's what you have in a column store. The data is stored in columnar format. So this is your fact table, where you're going to do large-scale aggregations. That sort of data sets is what you'll store in the column store.
So what's your typical size of the file?
So the question is, what is the typical size of the file? So we have a parameter in the database that you can tune to choose a smaller or larger file size for each one of those files. It's now 1 million rows per file. Previously it was 100,000 rows per file. And if you do decide to change it, you can change it also. The default is 1 million rows per file.
But that's in terms of rows. I mean, size of the row can be also there.
Yes.
What's the typical size, practical?
It totally depends on the data type you choose, right? Because you're storing each column. So the question is, what is going to be the size of each file typically? And the answer is it's going to totally vary on the type of data that you're storing, the cardinality of the data, et cetera, right? So if the data type is varchar 256 versus 1024 versus something else, if it's an integer or something else, those things are what are going to determine the size of those files. I couldn't just pick a random number and give it to you because it wouldn't be accurate.
Okay, so what is the typical or maximum? What's the maximum size of the row that support?
There is no such limitation on the row size or column size.
So let's say the row size is 1 megabyte, and then you make 1 million rows as a typical example. So does it mean that it will be over a gigabyte file? Typical file, is it practical or it's not practical?
So great question. So the question is, if you have, let me paraphrase the question and say, if you're storing data in the column store, in the files, if you're loading a megabyte per row or whatever your payload size is, what is going to be the size on disk? So one thing that I didn't touch upon actually, and I just basically said encoded and compressed and whatnot. So what typically happens with data that you're loading into the column store is we will store all of the data in columnar files. Because we encode the data, you also get a lot of compression. So if it's a megabyte that you're loading, well, it's too small a size to do math on. Let's say you're loading a terabyte of data.
Let's say we're dealing with binaries, so that are not compressible much.
It totally depends, right? So what you're doing, what sort of data is there, right? So in this case, let's say you're loading a terabyte as a general example, right? You're loading a terabyte of data. At a very general metric is you get 5 to 10x compression when you're storing it on disk, because the data is going to be encoded in a set of files. It'll sort the data, it'll encode the data, and it'll be stored in a set of files. Whether it's binary data, whether it's integer data, it does not matter. right? We'll try and sort whatever data that you're loading into those files, and we'll try and encode it. Whether it's run length encoding, dictionary encoding, some other type of encoding, it will be applied. There's a whole bunch of encodings we support. So that's what's going to provide you with the compression in the agent, right? So now, when you're encoding and storing the data, the value there is that if you're pulling a set of files, I gave the example of the set of sales for a certain region, for a certain sales rep. You're pulling that, you can pull an entire file into memory, and then when you're trying to run further queries, if you can resolve those queries in that large file, then you're in great shape because it's encoded. You're storing the encoded data in memory. So you can host a lot of that encoded data in memory, right? So if you're accessing a large set of data from column store, a lot of that encoded data can be sitting in memory. So you're loading a raw terabyte size data set. Let's say you get 5x or 10x compression. For the sake of math, we'll say it's 10x compression. So terabyte will drop down to 100 gigabytes, and that's what you're using in memory, right? You can almost host the entire data set in memory because of the encoding and compression that you get.
It's very rarely that text is compressed to 5 times. If it's binary, it's not compressed
Yes,
at all.
so it is going to vary. That's why I said 5 to 10x compression. It's going to vary based on your data, based on the cardinality, based on the columns, based on things like that. Typically, 5 to 10x compression is what we see. Any other questions? Please go ahead.
Yeah, so with this kind of architecture, so let's say there's a single table and you want to run transactional and analytic queries on, you have to store a duplicate of it in memory at all times?
Yes.
Okay.
So sorry, let me repeat the question. So if you have a single table that you want to have in memory and on disk, would you duplicate that table? It totally depends on your use case. So let's say that you're trying to do, so that single table can serve multiple workloads, right? So let me start with that. Rather than just saying yes, let me answer the question in more detail. Let's make sure we have time. So first and foremost, you can choose on a table by table basis whether it's a row store table or a column store table. Let's say you make a choice, you would choose what is the majority of the operations that you run on the table. That defines what type of table it is. There is nothing preventing the row store table from doing analytics. There is nothing preventing the column store table from doing transactional querying. What will happen is you're going to pay a penalty in one form or another, right? So if you're doing analytics in the row store, you're going to do dirty reads. If you're doing transactional querying on the column store, you're going to assemble all those columns together and make them a row, right? So you can choose to create the table in a single location based on what the access pattern is like. So if you know a majority of your access is going to be transactional, it'll be a row store table. If it's majorly analytical, it'll be a column store table. You can also choose to make it row store and column store, and you can load both the tables if you so choose. If you feel like you're paying too much of a penalty, but that's not very common, right? So for most cases, if you're looking to do analytics and the data is sitting in memory, typically it should do fairly decently, right? What happens typically is, the next slide touches upon this, is the size of data sets that you can store. There is a limitation on the amount of data that you want to store in memory, because memory is cheap, but still not cheap enough compared to disk, right? So your high value data is what you'll store in your row store, and transactional data is what you'll store in your row store. In your analytical store is where you'll have petabytes of data. And your row store is what you'll have gigabytes, single-digit terabytes, sometimes double-digit terabytes of data. All right, so even that will determine, the size of your data set will also determine where you host it. Does that answer your question?
Yeah, it's just more like, let's say you have a workload that's very heavy on analytic and transactional, like your main sales team or something like that. As you're learning about like the sort of like, if you're having to sort of duplication, we run into that same sort of ETL question that we're kind of trying to address.
In that case, if that data is of high value and you're willing to put it in memory, put it in memory, right? Where is the majority of your transactions? If it's absolutely split down 50-50, put it in memory. And then it just becomes a question of how much memory is available, and you're good to go, right? You do not want to run select start queries in column store too frequently because you're assembling all those columns together every single time, right? We can try and optimize it, but there's not much more that you can do for that. So in that case, choose row store column, is what I would say. Okay. Any other questions or comments? All right. So I think I touched upon everything here. This just talks in more details about the concepts we've discussed already. What does our architecture look like when you go to deploy MemSQL? So before I talk about the architecture, one thing I want to touch upon is the architecture looks like it's distributed. It's shared nothing MPP. What happens when a user is querying your database? Do they see all of this complexity, or do they see there's a lot of nodes, or what's going to happen? Nope. From an end user standpoint, they're querying a database and they're querying a table and they're running a query. They do not see an entire cluster. They do not know if a table is in memory, is it on disk. Unless they have access to the metadata, they wouldn't know that the table they're accessing, whether it's a fact table or dimension table, where is it stored. Right? They can make educated guesses based on, this is a fact table, it's probably, on disk or a column store. This is a dimension table, this is sitting in memory. That's the level of guessing that they can do. But typically a table doesn't look any different. So from Tableau or any other BI tool, you just drag and drop stuff. All right. So that's what our architecture looks like to an administrator. So you can see that. Are you guys familiar with Hadoop architecture? Anyone familiar with Hadoop? I see one hand up. That is surprising. 6 hands up. All right, people are being shy. So I'll assume you're not being shy, so I'll touch upon this in a little more depth because you didn't raise your hand. So MemSQL has 2 types of nodes, aggregator nodes and we have leaf nodes. Aggregator nodes are similar to Hadoop's name nodes. If you don't know what Hadoop's name nodes are, I can talk about that, or basically it's easier to talk about MemSQL. So MemSQL has aggregator nodes. Aggregator nodes store metadata about the data. Aggregator nodes service your queries. Aggregator nodes distribute the data that you're loading amongst the data nodes of the cluster. Right? Hadoop has data nodes. Those data nodes are leaf nodes in MemSQL. Right? So the aggregator nodes are going to store metadata about the data. When you run queries, they'll create distributed query plans. When you load data, they'll distribute the data based on your shard key and other things across the cluster. The leaf nodes store the data of your cluster. You would typically never query the leaf nodes, right? So as an administrator, you're just monitoring, making sure you're not losing your leaf nodes, they're not going offline, things like that. From accessing the database perspective, you access the database through the aggregator nodes, and it's round robin, right? So you want to distribute the workload across all the aggregator nodes in the cluster. That way you're leveraging our MPP capability. So if you're coming from Oracle or other databases, don't just go connect to one aggregator and say, all right, this is our entire workload. You want to distribute that workload, and there's JDBC parameters that say, okay, round robin the workload if you're connecting through Java or some other tool, right? It's just a comma delimited list is all we require, and we'll round robin the workload across the aggregator nodes. Now, the leaf nodes, you can see that they're distributed. So they store the data, and you can see that they're distributed into 2 availability groups, right? So what this does is it provides high availability. So let's say, I think the next slide describes this much better. So let's just go to the next slide. So let's say that you have a shard O1 on leaf node 1. Let's say that you lose this leaf node. You have the same shard available on this leaf node in another availability group, right? So this is high availability. This is something that you can turn on in MemSQL. What happens when you turn this on? We keep a replicate of your data in the cluster. So in this case, if you're loading data in one availability group, it will be replicated to the other availability group. So
who holds the information of where the shards basically distribute? Do you have something comparable to research manager, node manager, and all the other Hadoop stuff? Or
so the question is, who keeps track of what is kept where and how things are sharded and things like that? Do we have an architecture similar to Hadoop? I would say we have similar concepts to Hadoop, but our architecture is much simpler. So we don't have to do resource management and things like that. We don't have multiple processes running so you need a yarn resource managing tool and whatnot, right? So in our case, the aggregators store metadata, right? So when you're trying to access data, a query comes into the aggregator. The aggregator keeps track of what leaf nodes. The leaf nodes also tell the aggregator, I'm alive, I'm alive, I'm alive. If in a certain time frame the aggregator doesn't hear from the leaf node, it knows that this leaf node is offline. then it will automatically send any other workload that requires access to the shards of this particular node. It will send that workload to this node because this has the shards, or some other node, whatever it is, right? In this case, ON1 is here, ON1 is here, so it'll send the workloads to this node.
So one leaf knows about another leaf, or leaves do not know about each other? If leaf 1 is down, it goes back to aggregator to decide to go to another leaf, or leaves knows about each other?
It is the aggregator that does the management. Because you do not want leaves handing off, right? Because you have multiple scenarios that occur. They are, what's a polite way of putting it? Networking hiccups that occur, right?
So aggregators are basically managers of the leaves.
So the question is, aggregators are managers of the leaf nodes? The answer is yes. The aggregators are the brains of the operation. A simple way of looking at it is that leaves are dumb. Well, they're not necessarily dumb, but for the sake of this example, they're dumb storage units.
So what's the function of leaf besides to provide the data to aggregator?
That's all. So what's the function of the leaf? The leaf stores the data and provides the aggregators the data that it's storing.
So leaf don't do anything but just
Leaf does
data.
other, so I'll touch upon that as we go further. So the question is, what else does the leaf do? So I'm going to touch upon that as we go further. Let me just wrap up this concept, and then I'll address your question further. Right? So there's another question.
Just a quick question. The reads and writes the affected for these replicas, like data?
Sure.
How does it work with ACID?
Sure. Good question. So the question is, are reads and writes affected by these replicas or not? Right. So give me maybe 30 seconds and I'll answer your question. I just want to make sure I wrap up this concept so people understand it. Then I'll answer the questions that you have. Right. So in this case, you can see that there's replicas available, and this is a very simplistic representation where one exact fragment is available on another node and whatnot. This is just to show you how data is sharded and how it's distributed, right? What happens underneath the covers is every single table is sharded, data is distributed equally amongst the nodes of the cluster, then it's replicated in availability groups, right? Clients have set up these availability groups in such a manner that you can lose entire racks in a data center. So if your cluster becomes large enough, we have clients running 200-300 node clusters. In that case, rack failures also become a possibility, right? As your cluster sizes increase. In this case, you can lose an entire rack, and because of the way that availability groups are going to be set up, you can ensure that if another rack has the shards of data you're looking for, your database stays up and running. You need to fix the rack that went down, but your database does not go down, right? So that basically builds up the concept here. Now, your question was what happens with this replication, right? So there's multiple levels, multiple options you can choose when you're replicating data between your leaf nodes. So you can choose to do async replication, right, which is one option where you say, okay, I'm loading, for the sake of simplicity, the shard O1, and I want you to asynchronously replicate it to another node. And then, if you lose power in between, you're at risk, right? Because if the replication hasn't completed, then you may lose that data set. You could turn on sync replication, which is also another feature available in MemSQL. And basically you say, okay, I write this shard here, do not return a commit until that shard is replicated. That's another option that's available. So it's up to you what you want to choose. If high performance is the biggest consideration, and you can always reload the data that's missing, in that case choose async replication. If you're okay with your commits taking a little longer because it's going to sync replicate to the buddy node, in that case you can turn on sync replication. Does that answer your question?
The second part of the question, the async replication, how the ACID compliance will work because if the node is gone and durability is gone.
Yes. So the question is, with async replication, what happens if with the ACID compliance, if the node goes down? The answer is you're taking that risk, right? You're saying I want the, so maybe I'll talk about the customer examples here. We have clients that have requirements that we want to run. So there's a bank in New York that runs their private wealth management portal off of MemSQL. So I got to be careful what I say. So I'll pause and I'll think and I'll speak, right? So the private wealth management portal runs off of MemSQL. their requirement is because these are high net worth individuals, there should be no spin, right? There's no hourglass which is spinning and they're waiting for the data to refresh. So MemSQL has to return those result sets in 200 milliseconds or less, right? Ideally, it should be less. 200 milliseconds is the max because the remaining up to a second is for rendering by the website and intermediate layers when the client is refreshing the dashboard, right? So for those sort of use cases, they're like, we do not care about sync or async. We want the best performance possible. We can always reload the data because it's sitting in Kafka, or it's sitting in some other location where we can refresh it, right? If the data is, for example, ATM machine data, you do not take that risk. You say we want sync replication, right? So there's multiple scenarios, and based on the scenario, you can choose what level of asset compliance do you want. Any other questions or comments? I see a raised hand.
Is it possible for one aggregator to hit one availability group, the other aggregator will hit the other availability group for the same week or the same data set?
Typically, we will stick to one availability group. Again, lots of caveats depending on sync, async, etc., right? Typically, we stick to one. The simple answer to that is we stick to one availability group.
So if week A goes down and then its replica A prime is then seen as the source of truth for that data, then A comes up. Is there not a case for A prime and A to be hit at the same time?
Okay, I forgot to repeat the question earlier. And by the way, quick thing, this is blinking red, so I guess it's still recording. No issues, right? Okay. All right, so your question was, and I forgot to repeat your last question, so I'll repeat the question. This question here is, what happens if this leaf goes down and your aggregator redirects everything to this leaf, which is a replica of the previous leaf, and then this leaf comes back up. So the aggregator, because it's the brains of the operation, it says, this went offline. There could be multiple issues, right? There's a hiccup in the network, someone decided to restart it, something happened, right? It may have gone down for an hour, it may have gone down for longer. It may have gone down for a couple of seconds, right? So the aggregator says, okay, this is offline, let's direct everything to this leaf because this has the replicas. Yeah, this has the replicas. So because this has the replicas, this is now the most updated copy. Let's say this leaf node comes back offline, it will not be available for querying until the aggregator says these two nodes are now back in sync. So now this will catch up. And once it's caught up, then it says, okay, I'm up and running, I'm available, and I'll become the master again. Does that answer your question?
Yes, but a follow-up, and because there's multiple aggregators scaling out, can the aggregators ever disagree on these data?
So the question is, can the aggregators ever not agree that one node is a master or not? No, because the aggregators are kept in sync. So the aggregators, when you commit data, anything, the aggregators are in sync because you have failure scenarios where an aggregator may go down. You do not want a scenario where one aggregator thinks this is the master, this is the master, another thinks this is the master. So they stay in sync about that. Any other questions? I see another hand raised.
The row level and column level, do they see on the same nodes or do they sit again in different nodes?
The question is, do the row level and column level data sit on the same nodes or different nodes? It depends on what you're doing, which may touch upon what I was going to talk about on the next slide. We may have to breeze faster after this. I'll pause the questions because we want to wrap up by about 8:20. So I want to make sure we have sufficient time for the demo also. So the data in a given table, whether it's row store or column store, may be sharded or may be a reference table. If it's a reference table, it's replicated across all the nodes in the cluster. Simple example of a reference table is date dimension. Does not make sense for the most part to shard a date dimension because it's so small, right? You do not want to now have multiple shards of date dimension sitting and then you're moving those shards across because it's so small. Just reference, make it a reference table. You have a fact table, you want to shard that table and you want to shard it and distribute the data equally. So a given node will hold a given shard of the table, but not the entire data set. A combination of multiple nodes in a given availability group will have the entire data set for that given fact table. Does that answer your question?
Yeah, this is interesting, but before you mentioned that some data sets are stored as code, where some data sets are stored as kind of row level. So basically, are there any dedicated areas? So, but it's just they can be distributed equally.
So the question is a row store table or a column store table going to be located in a dedicated area? The answer is no. It's going to be sharded across multiple nodes in the cluster by default. Well, by default, based on a primary key, we'll shard it. Right?
Is there a specific way to choose whether it will be column oriented or row oriented?
Yes. So the question is there a way to choose if a table is row oriented or column oriented? The answer is yes. When you create the table, you will choose whether it's a row store or column store. The syntax is different.
So I can choose.
Yes.
Not
The question
system.
is,
It's not the system which is choosing. I am choosing.
the question is, do I make the choice or does the system make the choice? The answer is, you make the choice. The system will not automatically switch things around for
And
you.
if I don't want to make a choice, I want the system to make a choice.
If you choose nothing, then the system will make it a row store table.
A row.
Yes, because it says you do not know
So
what you
there is
want.
no any specific intelligence that will kind of differentiate factual from dimensional tables based on some kind of pattern.
So the question is there some sort of intelligence which says change this table over from one type to another? The answer is no. We keep it up to the administrator to choose what type of table you want because you know the data best. The way you're accessing the data may be transactional today because you're loading the data in and you're figuring out is it valid, etc. And it may change over time. And we do not want to make the choice for you, saying, hey, I know better. Let's just switch it around for you. And also that affects the performance aspects of your database too, right? So if things switch around, the query is running in 10 milliseconds today, we switch it to column store, it takes 20 milliseconds, you're not going to be happy. So for the consistency use case also, we will not switch things around. I'm going to have to cap it here for the questions because I want to try and get to the end of the deck. So redundancy. There are 3 levels of redundancy in MemSQL. One is RAID. The failure of a single disk does not lead to the failure of a single node. Second level of redundancy is high availability, which we just discussed. The failure of a single node does not lead to the failure of your cluster. The third level of redundancy is DR. So we will do replication between a given database as a master to another database as a slave. We will ignore any GDPR or any other data locality concerns with this example because it's simple. In this case, you have an Americas cluster which has a DB1, which is a master database. You're replicating it to your EU cluster. In EU, you have DB3, which is a master. You're replicating that to Americas. So in this manner, you could have a given database be a master, another given database be a slave. You can make an entire cluster a master in that manner by creating every single database as a master and replicating to another cluster where everything exists as a slave. Right? So this is the way you can set up redundancy at a cluster level where disaster recovery scenarios are addressed in this case.
Do you support master-master?
The question is, do we support master-master? The answer is no.
No.
No. The reason
It's always master-slave. Master and other slaves.
so
One master, many slaves.
yes. So basically, we do not support hot master-master because that affects query performance. If you're running a query in a given cluster, this is a great example of it, across multiple continents also, you do not want to incur a penalty because your data set is not committed in your other cluster. So in this case, we will do asynchronous replication. If you want to set up master-master, you will dual load from your application into 2 clusters, and that's the way you'll have 2 masters. And your application will resolve where the data is loading and how.
But you can have master-master with asynchronous. So do just master-master with synchronous. Whenever it will come, it will come.
So the thing is, you can the comment is you can still make it master-master. When the data comes, it comes.
Theoretically, I mean, I'm not
Theoretically.
saying your product because you know your product and I don't.
So
but
the challenge is with theory. In theory, if they're not absolutely in sync, they're not master-master. If they're async, they're not master-master. So we will push the data as soon as we can. We have a client which has a T1 connection between two data centers, and I'm really running late on time. But anyways, so if we have a T1 connection between two data centers, we have clients that have less than 5 to 10 milliseconds lag between, even using asynchronous replication between two data centers. But that's a telecom client, and they can afford to set something up of that sort. For anyone else, this is not master-master, right? Because it is asynchronous. In those 5 milliseconds, if you lose a cluster and it's not replicated over, you do not have a master instance which is up to speed with the cluster that went down, so we do not call it a master. I can be a sales guy and say it is a master, but I won't do that. Lastly, if you've used Oracle, Oracle has Enterprise Manager. This is our Enterprise Manager equivalent. You can use a web-based GUI to administer your cluster. You can run queries in this. You can view your query plans. You can see what's the health of your cluster. If you're loading data, you can see how the loads are going, etc., etc. There's a whole bunch of features and functionalities that we provide through a GUI. For people who like to use a command line, you can always use a command line. Use the MySQL client. You can access the data set using a command line editor. You can use, I will show you a couple of different examples how you can basically access the data set. It's not exhaustive list, but it is some examples of how you can access the data set in MemSQL using SQL Pro and a BI dashboard, etc., etc. So I will not pause for questions here, and I will just go into the demo now. Let's give it a couple of seconds. All right, so let me just maximize everything, make sure everything is still running. I've had a couple of issues with the display, so I want to make sure everything's running. All right, this looks promising. All right, so what I was going to do is show you a demo. And what the demo does is it shows you stock trade data streaming into the database via Kafka. So we will set up a pipeline to connect to Kafka, ingest the offsets into MemSQL. You will see it being ingested, right? And then you can run queries at the same time on the dataset while it's loading, right? So as the dataset is loading, I think I'm going to load like 30 to 40,000 records per second into the database, and I have a really small cluster, which is why I'm limited to that. What I've spun up here is the M5.2XL instance type of AWS. So I have 8 vCPUs and 32 gigs of RAM. I have 3 of these with 1 aggregator, 2 leaves, really small cluster. And what I'm actually doing is showing you a modification of a demo that we have in our documentation, which is stock trade demo. So let's go to the command prompt because I want to show you a couple things. So you can see here we have Kafka and Zookeeper running. Now let's make sure it's still running. Yes, it is still running. What we're going to do is this is running. I'm going to say I have a small script that I have here, which is going to spool data. It's reading from a flat file. For the sake of this demo, I didn't have a streaming source of data. So I'm reading from a flat file, putting the data into Kafka at 30 to 40,000 rows a second. That data will then be ingested into MemSQL. So this is going to spool the data right here. I'm trying to do this with one hand, so this is the fastest I can do. So we have a GUI with which you can create pipelines to connect to Kafka. So in this case, I'm going to, so basically here you see what the cluster looks like. We have a master aggregator, we have a leaf. You can look at CPU, memory, disk, capacity, disk utilization, network usage, etc., etc. Multiple metrics are available here. You can look at the schemas which are here. We have a couple of different demos that we do. This just has a couple of different demos. Here you can create a data source. I'm going to create a pipeline. Am I in your way?
No.
All right, so showing up well? Yes. So I'm going to create a pipeline. So what's happening right now is I'm typing with a single hand as fast as I can, test pipe. What's happening is I'm spooling data into Kafka, so it's buffering all of that. So what you'll see is a big spike when it first starts loading, and then it'll basically level off. So I'm creating a pipeline. It says create pipeline, give me a name, test pipe, continue. It says give me the Kafka broker. I'm going to copy the IP address from here so I don't fat finger it. Paste it here. I know the port is 1992. The Kafka topic is test. And now you get an option. Do you want to start from the first available offset per Kafka partition or start from the last available offset per Kafka partition? I'll just choose from the start just to show you the spike. Here, in the next step, what you can do is you can add a transform function. So what a transform function does is on a batch by batch basis, you can execute custom logic of your choice in a language of your choice to modify the data. Now, you're limited by your imagination as to what you can do here. The simplistic example is you have first name and you have last name. You want a full name. You can just say, okay, tie these two together. More complex example is you have first name, last name coming from the stream, and you want to merge the first name, last name with a set of orders which is sitting in Oracle database. By means of connecting to Oracle through this transform, you can merge the data together and load it into MemSQL, right? I won't do a transform here in the interest of time. I'll just hit continue. Now it says, select an existing database or table. What am I loading this data into? I'm going to load it into the test database. I'm going to load it into the trade table. Now it basically gets the trade table metadata. It says, these are the columns in the table. How is your data formatted? And I have a custom format because I happen to choose a pipe. I say this is a pipe. You can choose how your fields are escaped by, fields enclosed by, line started by, etc., etc. I'll leave the rest as default, right? Then I hit continue. Now it says you want to test pipeline? Sure, I absolutely want to do that. If this fails, well, I have a lot of work to do to fix the demo. But basically what it says is, okay, I connected to an offset and I can see here, this is what your data looks like when it's going to be loaded into the database. You can see there's an ID, trade ID, there's a stock symbol, there's a number of shares purchased, there's a shares price, there's a trade time. Now, this is all fake data. I'll hit create pipeline. I'll say creating pipeline. And pipeline is created. And right away you can see that the database is now ingesting data. So the cool thing about this is you don't have to write code to basically connect to Kafka and ingest data. If you want to write code, the code looks like create pipeline test pipe for table trades. Connect to this Kafka broker, this port, and this is the topic I want you to ingest, and this is what the structure looks like. Literally what I did is, and actually before I lose this, so this is 2 million rows were loaded, then 30K rows, and now you can see it's fairly flattened out. We're loading 30 to 40,000 rows a second. So basically, this is how you're loading data into the database. You can choose, what format your data is in, if you have JSON data, etc., etc. There's a lot of features and functionalities and bells and whistles in terms of the ingest process. You can transform the data as part of a routine you guys write, whether it's Python, Perl, Java, or any other language of your choice. Or you could say, I want to use a SQL construct. So what I want to do is a target of this pipeline should be a stored procedure. And then before loading the data from the pipeline into a table, I want to transform it and maybe split it up into 2 different tables. You can do that too. So there's a whole bunch of things you can do as part of the ingest process. Now this is cool ETL functionality, but we're not trying to take the place of a tool like Informatica, because we're not going to try and say do all your ETL processing in MemSQL. We can do ELT really well because we have column store and row store capabilities, but we're not an ETL engine. So if you're looking to do large scale transformations and a whole bunch of other things, you may want to leverage your ETL tools for that purpose. But if you're looking to do things of this sort and save money, and you don't do large scale transforms and whatnot, you can use the database for that. So this is going well. What this shows you is there lag. There's like a 3K lag at some point was there. Again, I have Kafka running, MemSQL running on the same node. So occasionally there'll be a lag. in the ingest. This lag has gone to 0. We're ingesting 30,000 rows. We're parsing 23,000 rows. We're writing 21,000 rows, whatnot. So there's a lot of ingest going on. Now, let's run a couple of quick queries. Okay, I'll do this with one hand. Let's give it a couple of seconds here. Exit. And we'll do queries maybe. LS. So I have a couple of queries here. So this is just some pre-written queries, just so that I don't have to sit and type SQL query here. So this query will find the most traded stocks. It'll run really fast over a whole bunch of data. Oh, this is single-handed typing is no fun. So no, it's all good. Can you guys hear me in the back? All right, I'll just speak loudly. Oh, it won't work for the recording, will it? So for the intents of the recording, I'm just typing something. I'll come back to the mic. Let's skip that. So I have the same queries here, so that I don't have to do all that work. So I'll just show you through the GUI. What's happening is the same thing here. In the command line or the GUI, I have this most traded stock query here. I can run this query real quick, and you can see the response is fairly instantaneous, right? I have limited it to 10 because I don't want to show you millions of rows here. No point in doing that, right? These are some of the top 10 most traded stocks. The most volatile stocks, it can show you what are the most volatile stocks that are being traded right now, right? This is a day-old data. I loaded it yesterday. This portfolio aggregation query basically checks the average price per share, the min price, max price, what percentile does it fall under, and it runs a fairly large calculation. In this case, it took like maybe a second, maybe a little more than a second, who knows. Under a second, basically, for the most part, is what happens here. This portfolio analytics query is showing you all of the information you're looking for to basically look at your portfolio, compare it versus quarter over quarter, look at the percentile differences for your stock portfolio. So you can run a command line query to do the same thing. I'm just not going to do it because it's a lot of typing with a single hand. What you can also do is you can put any dashboard of your choice against it. So in this case, I had run this dashboard when there was no data. I'm going to refresh this. Now this is Google Data Studio, which is running in the cloud. So this basically may take a little longer to refresh because it's connecting from GCP over into AWS. But basically, it's similar information that's refreshed here. You can use, I'm using a MySQL driver here to connect to the MemSQL database. And you can see the same information graphically. You can look at the pie chart. You can compare what is the max price versus the average price if there's a big deviation. You can slice and dice all of the information however you choose. So while we are running these queries, what we should do is see how the data is growing, right? So I expect that a couple of million rows should have loaded by now. So use test, that was what we're loading into. Hopefully I have this in history somewhere. Here we go. So we have 5 million rows loaded, right? So this is not a static demo. You got more data which is being actively loaded into the database. So this is a very common use case with our clients where they want to stream data into the engine in real time and be able to run queries in real time against the engine. This is a mock example of what the private wealth management team is doing for a large firm in New York. Of course, we cannot replicate their dashboards because they have a whole bunch of drill downs and things like that you can do. But this just shows you the power of MemSQL. One of these tables is a row store table, another table is an analytical table, and we're running queries across that. These select count stars are fairly quick. You can run those other queries and they're fairly quick too, right? So as I showed you previously, it doesn't take minutes or hours basically to run these queries because of our modern architecture. So that was the real quick demo of how financial services firms are leveraging MemSQL with fake data. I'll pause here and see if there are any questions or comments. I see a raised hand.
In MemSQL, can you give a query plan?
Absolutely, you can view the query plan. I haven't spun that up, but basically you can spin up the Studio UI I showed you earlier, and you can. No, this is just an IDE. I'm using SQL Pro. It's not our IDE. I just wanted to show you. You can use any IDE out there, like SQL Pro or DBWiz or Squirrel or something else. As long as it has MySQL compatibility, you can connect to the database.
Can you show the plan for that query and probably show plan and then select everything?
I'll have to just profile and do show profile. So you can do explain. You should be able to do it. I didn't write it down. There you go. Let's see how this renders it. That's the query plan for that. If you want to look at it in a pretty, tree display manner, you use our ID, our tools, and basically we'll show you a nice visual representation of the plan. You want to do it this manner, you can use the command line also and say, profile query, show profile, explain, etc., etc. You can do show profile JSON. It'll show a lot of details about every single step. What is the statistics that are underlying those sort of operations also. I see a raised hand. Any?
So you mentioned that kind of you do work with other ETL tools. So the question is, do you have connectors like a bulk connectors, maybe like sharded connectors, so that, for example, if you have a ton of data, a terabyte in MemSQL, take it out in a kind of a parallel way, like in a bulk way as well, and then do some computation to put it back in. Do you have patterns like that?
So the question is, do we have the ability to do? Let me simplify. Does MemSQL have the ability to do parallel export, parallel of data? Yeah, export and import of data. So yes, parallel import. There's a couple of different ways you can do. There's load data, and I will show it here. Load data, basically, you can land the data on your client. You can land the data on a MemSQL node, aggregator node, and we can ingest the data from that given node. So, but in that case, you're only leveraging the capability of that individual node CPUs to parse that data when you use load data, right? If you do load data from your client, you're leveraging your client CPUs, which is really not going to perform optimally. You can leverage pipelines to connect to a file system like a SAN and ingest data in parallel. You can use pipelines to connect to HDFS, ingest data in parallel from HDFS. Kafka, ingest in parallel from Kafka. S3, Azure Blobs. That's what you'd use for large-scale ingestion of data. If you want to do export of data, there's the parallel export tool that we provide. It's available on GitHub. You can just basically use that to export the data in parallel. Parallel export UDX or something. It's
When you look online, just works with MySQL.
yeah. So MySQL parallel export. Yeah. So that's what you. Yeah. That's what you basically leverage to parallelly export your data from the database in multiple connections and whatnot. Any other questions? I see another hand raised.
Are there any query performance issues once you reach like millions of rows, maybe like 10 or 100 million rows?
Great question. Is there any query performance issues if you have reached 10, 20, 30, 50 billion rows? The answer is no. Because when you're accessing your data, we have a lot of metadata available in memory. So we'll resolve your query in memory to the data set you're trying to access, right? Where your performance will be affected is you say, select star, all my 50 billion rows. Good luck. You're going to stream the entire data set and it'll keep streaming. Yes, your performance is going to suck because you're just streaming the entire data set. If you're doing an analytical query where you do an aggregation across this data set, you're going to provide parameters you want to filter against, and that will be applied to your query, and which is why your query performance is not affected. And because we're a shared nothing MPP system, you can scale out your leaf nodes to service data growth use case. You can scale out the aggregator nodes to service concurrency use case. So depending on where your limitations tend to be, So let's say you have a lot of concurrency occurring as the dataset volumes are increasing. You can increase concurrency individually from your data growth. So you can service those use cases there. Another question?
If you perform applications over time series data, so you have to load all the data into memory and then perform all the applications.
The question is, if we have to do aggregations over time series data, do we have to load the entire data set in memory and perform the aggregations there? We will not do that. We do predicate pushdown. We operate on encoded data. We will only pull the data which is required for servicing your query into memory. And then even then, we will operate on the encoded data until the final results are broadcasted to the client. Any other questions or comments?
So what if there's not enough memory, for the data? If the data set is bigger than the memory available, how do you deal with that, or you don't deal with that?
The question is, if the data set is larger than the memory available in the system, what happens then? So we have two parameters, max memory, max table memory. Once you hit, let's say you're loading data into table, you hit max table memory, you'll not be able to load more data into memory. So that limits what you can do with the memory there, right? So we won't just spill to disk because your performance is going to be affected. We want you to make conscious choices of what you want us to do, right? So yes, there is a limitation on memory available, but in that case, you can choose to either increase the memory, one, or you say, okay, I really want to load this data set. Maybe I convert it into column store table and access the data set in that manner.
So I didn't quite get it. So if the data set is bigger than memory available for your cluster, or your perceived cluster, do you deal with this situation, or you just refuse to deal with this situation? So I have the data set, let's say for 10, whatever, gigabytes, and I have 1 gigabyte memory. Can I run MemSQL on that, or MemSQL cannot run that?
Absolutely. So the question is, if you have 10 gigabytes of data and you have 1 gigabyte of memory, can MemSQL run queries on that data set? The answer is, if you make smart choices, yes, you can. You choose a column store table, you load the data into the column store, it's going to be encoded, and it's not going to pull the entire 10 gigabyte or 10 gigabytes of data in memory. You will only access the data set that you're accessing from disk, pull it into memory in encoded format, which lets us host a lot more memory in data in memory because you chose column store. Now let's say you choose row store and say I want to load 10 gigabytes of data in 1 gigabyte of memory. After it fills up the gigabyte, it says I'm done. I don't have any more memory to throw at it. Choose a different table type or delete the data.
So you're saying that row-based tables are loaded entirely in memory, and
Yes.
column-based tables are loaded part by part into memory for the processor.
That is correct.
That's what you imply.
Yes.
Right? Okay. But what if I need to do the joins and I have like 2 tables which are bigger than whatever memory is available?
Then the query will fail.
Going?
The query will fail unless you enable spilling to disk, whatnot. If you spill to disk, anyways, your performance is going to suffer. So
Right, but even with performance suffer, will I get functional results?
you can, yes. You can. It depends on the resources available. Do you have sufficient disk space available? Have you enabled spilling to disk? Are you even bypassing what's available on disk if you're doing a Cartesian product, etc., right? So a lot of parameters go into that, but the answer is yes. You can service that workload. Your performance will really suffer. In that case, you should be making smart choices about the schema you decide on.
Do you have your clients which are working with big data sets of data?
The question is, do we have clients working with big data sets of data? We have clients running with 10 terabytes of data in memory.
But
In memory. We have clients running, I think, what was the number? 300 terabytes of data across memory and disk, right? So not all of it is sitting in memory because they're using column store for the majority of the data. We have 300 node clusters. We have very large clients which are leveraging MemSQL. Typically what happens is they basically scale out based on the needs and requirements. So we have no limitation on you can only scale to this many number of nodes or this much data or this much row store or this much column store. You're limited by the resources available in the system.
so how do they make their smart choices? You're saying they need to make smart choices.
Yes, the smart choices is knowing what you're doing with the engine, right? So you can try to automate a lot of stuff, but you cannot prevent people from shooting themselves in the foot, right? So as a person, if you choose and say, I want my entire data set in memory, and I have a gigabyte of memory, and I'm going to load 10 terabytes of data, defies the laws of physics, right? You can't load that no matter what you do. You can spill to disk. Do you have sufficient disk, right? So those sort of concerns come into play.
Your software
Sourabh, you got 2 minutes. Then you take it offline.
Sure. Let me take this offline. I know there was another question. You raised your hand.
Regarding compliance, can we encrypt data at rest?
So we support looks encryption. So that's how it's encrypted on disk. The next question typically is what happens in flight. We support SSL within the cluster, between the cluster and the client also. Any other questions? I see another hand raised.
If you like, create any visualizations or analytics, is it a good decision to get the data straight out of the database, or you need to have some analytical engine or service in between?
Great question. So do you want to have a caching layer between the database and a BI tool, or do you want to do most of the processing in the database? We tell you to do most of the processing in the database. Because you have an MPP system, leverage it to the best of its capabilities. You should not build caching layers in between, because then you have to refresh that, keep it up to speed, etc., etc. We support predicate pushdown from quite a few tools. If they do predicate pushdown, you will be running the queries optimally in the database engine itself, and you're leveraging our MPP capabilities.
And there won't be any performance issues.
Well, again, it depends on what your BI tool is running. Give me 10 billion rows of data, it's going to crash eventually. It'll keep streaming, it'll crash, but as long as the queries are reasonable, there should be no performance issues. So Click, MicroStrategy, Tableau, etc., Looker, Zoom Data, all of these integrate and work really well with MemSQL. Any other questions or comments? I was given a hard stop of 8:20, so I only have a minute left. Any other questions or comments?
How do you compare with other like Couchbase and
So the question is, how do we compare against Couchbase and other databases?
since you're not serious with that?
So I'll give a slightly humorous response and say very favorably. So there are a lot of tools and technologies out there which do very niche things, right? We only do NoSQL, we only do JSON, we only do etc., right? So what we've tried to do is provide you those sort of capabilities within the same engine. We can store structured data, we can store semi-structured data, we can store geospatial data. So we have done a lot of optimizations to provide you access to that data set. If the choice becomes how you choose is critical, right? Do you want SQL access to your data? Is most of your data going to be something you want to access through a BI tool? Do you want to have other use cases also addressed with the same engine? In that case, you choose MemSQL. If your use case is 100% NoSQL, object access, etc., then maybe we're not the right fit, right? So can we knock the socks off of other engines? Yes, if it's the right use case. And that's the non-sales answer, right? The sales answer is we will knock the socks off of everyone. Any other questions or comments?
Document-based data, it stores like the entire document in one cell, or you can actually drill into the document like a NoSQL.
You can drill into the document. Your query becomes lengthier as you do that, right? So you can access the entire JSON object as an example fairly easily and say, give me the entire object. But if you want a certain element, you have to basically qualify and say, drill down, and this particular element is what I want, right? So it becomes more complex, which is why I said if your entire use case is object-oriented or document access, maybe you want to go in that direction. If it is a hybrid sort of deployment, or you want SQL access, that's when you come to us and say, what's the SQL way of accessing this data set? And the SQL way is through qualifying the elements and walking the hierarchy in that manner. All right, thank you very much, guys. Really appreciate you making time.
Guys, where is the basket going around? Let's go. That's good. Has everyone got their card in there? Someone wants to win a Nintendo Switch, right? Do I have everyone's card? You have to be here to win. Do not leave. I can't say are those bright lights. Oh, sorry, it's blinding me those lights. Anybody else? Yes. Okay. Anybody last chance? Just give it to me. All right. Can I ask, let's see, can I ask you to mix up the cards inside? All right. Can I ask you, look that way, reach and pull out a card? You're really not looking. You missed the whole thing. Read it out. Read it out.
Tom Abraham.
Tom Abraham? Woo! Who's woo? Yes. Right. All right. Congratulations. Sourabh. I won. You won. Sourabh Mehta is here for one-on-one questions. Feel free to come on up now and ask. Thank you all for coming. Thank you, Sourabh.